Hey, good morning. So today I'm going to start chapter 10. Chapter 10 is on virtual memory. And there's some overlap between chapter 10 and 9, but they're actually distinct topics. So for chapter 9, what was covered was actually the idea of memory allocation, various types of memory allocation, and paging. But paging itself doesn't have to page out to a disk. And in fact, it could just be purely in-memory type of mapping. So you're mapping from some logical address to some physical address. In this chapter, by virtual memory, they talk about not only this logical to physical mapping, but more importantly, that you would page out to a disk and then page back. Okay. And so, of course, the motivation is very similar. In this, you start out with an executable program. When you want to run a program, do you load the entire program into memory all at once? We saw this last week or the week before too, in the sense that there's probably a lot of code you never really use or rarely use, or you won't be using until much later. So if you load the entire program, I mean, nowadays, look at how big your app might be, right? It could be hundreds of megabytes, if not on the order of maybe gigabyte. So those may take a while to load, and they take up a lot of resources. And so if you can load just part of the program, that actually can be very attractive. Why? Because most likely, once you load it, you can start running it, and then you load more in as needed. And we've seen dynamic linking, dynamic loading. Well, that was helpful, but those may require some management, either at the library level or at the user level, right? User code, they could actually call way to load in the dynamic linked library, DLL, and so forth. They could do that manually. But what you want to do is to be able to give that control to the operating system. So the OS can decide, well, if I want to load it or not. In fact, sharing too, because if you do your own loading, then the OS may not see what you just loaded, right? It doesn't see it. But if the OS has control, and then OS has opportunity to do sharing, right? Because, for example, your code would be the same copy across different processes. So you wouldn't have to keep redundant copies, right? So there's benefits to having OS take control of this task. And so in any case, you want the OS to help do as little work as possible so that it really is a better match between what the program needs and what the OS actually does and what the system can do. So if the program may be big in this executable image, but then at any given moment it doesn't need a whole lot of memory, then that's what you want to do. You want to keep it small. That way you can have better CPU utilization, and also you can have a higher degree of multiprogramming. That is, more programs can be loaded in there. So there's benefits, right? So that way your machine can be really utilized better instead of spending resources on things that it really doesn't need. And things get loaded in and loaded and unloaded over time. And so then also you want the user program to be able to run faster. And you might recall swapping, which was when the CPU or the machine is running low on memory, older OSs could swap out an entire process to make memory available, physical memory available. And if you don't really take up a lot of unused memory, then you wouldn't have to swap as much, right, or at all. So not doing swapping means everybody runs faster. And so having a virtual address space has another benefit, which is the fact that you present this nice abstraction to the program. The program doesn't really have to worry about running out of memory, ever, especially in 64-bit, practically speaking, right? And the program can have the view that memory address may start at 0 or some other place, and it's contiguous, and there's so much memory that you wouldn't have to worry about. And that's a nice programming abstraction. I mean, imagine that you have to manage the memory yourself as you write the program, having to allocate this chunk of memory, free it. I mean, you had to do that with malloc and free in C, and then if you do new and delete, right? And if you have to do that yourself, it's a hassle. And especially if you even have to manage the physical memory, not just virtual memory, right? And paging is done to allow the program not to have to worry about contiguous logical memory, right? It can think, I have an array, and with a pointer, it starts from this address, and no matter how long I go, there's enough it can do. But physically, of course, it cuts it at a page boundary and remaps them so that the user doesn't even need to know that those physical pages are all over the place, even though logically speaking, they're all together, right? You can just increment your pointer, goes on and on and on, right? But physically, they get mapped to different pages. And of course, having MMU is helpful in accelerating this mapping. And so now what is needed then is, well, at some point, you run a bunch of processes and you're likely to run into the physical limit. It's like your machine, how many gigabytes does it have? 8, 16 maybe? And now if you have a powerful PC, maybe hundreds of gigabytes. But at some point you still run out. And so what do? Well, that's when virtual memory can be taken to the next step, and that's really what this chapter means by virtual memory. That is, it still wants to maintain that abstraction that each process has its own virtual address space, and it doesn't just have to assume that, okay, I give you that big address space, but you only utilize a small part. No, it actually allows the programmer to utilize quite a bit. In fact, it could be larger than you actually have physical memory. Okay, and so this can be done by demand paging and demand segmentation. Now, demand segmentation was covered in the previous edition of the textbook, but since we went to the 10th edition, they pretty much took out demand segmentation because really nobody uses it in practice. So we're not going to talk about demand segmentation. We're only going to focus on the paging part. Okay, so to quickly summarize advantages with virtual memory, well, one is performance. You load program partially into physical memory, so you don't have to spend the time loading the parts you're rarely going to use or won't be using until much later or never going to use, right? Even though they're part of the same program. By using less physical memory, you can allow more programs to be resident in memory, running concurrently, higher degree of multiprogramming, also less straining on the physical resources, less need for swapping. And also process creation likely be done all in memory. In fact, with sharing, you can accelerate process creation. That's nice. And also programming abstraction, larger logical address space than physical. Programmer doesn't have to worry if they're running on a machine that may or may not have enough physical memory. The machine will figure out. It'll still support that abstraction so that it may have to swap pages to secondary store to make it available or load, unload behind the scenes. So programmer never have to worry about this kind of thing. And allowing several processes to share memory also. So if virtual memory is larger than physical memory, what do? Well, so you have the virtual memory here. That's what the programmer thinks they see. And the mapping here, but only a subset of the virtual memory can fit in physical memory. So what if you can't fit? Then, well, what the virtual memory system does is it stores some of these contents onto a disk. And of course, the disk is assumed to be much larger than you have physical memory, both for pricing reason and just, in practice, that's what people do. So your hard drive is still much lower cost than any of the memory you have, and it's going to stay that way for a long time. And also, disk is non-volatile, or should be non-volatile, and so that way, you don't have to worry about. You may have the secondary benefit of saving state and allowing it to be restored after some power outage. Now, a virtual address space looks like this, and of course, there's different versions of it depending on the OS. But generally speaking, a stereotypical view of this is you have text segment from 0 and up, right? Remember this from midterm question. What does text mean? It means executable code. Why? Because your interrupt service routines are likely to be in the very low part of address, and that's where you're likely to see with an OS going there, and plus some code, and because you do want the memory to be able to grow, right? And then linker also wants to start linking the code from lower addresses and up. And then after that, you place your data, and then heap is for dynamic allocation, deallocation. And then in the middle, you have the big empty chunk. And stack, we're not talking about 8051, we're talking about general Unix-like machines. They would grow downward from the high address down. Of course, if you run user threads, then your stack is not going to be just one chunk. It's possibly going to be in heap or some other places, several chunks of it. Certainly you can partition up your stack up there, okay? And just depends on how the OS supports it. Anyway, so stack grows down, heap goes up, and the hope is that the address space is large enough that they never crash into each other. That was the case for a long time until people starting to write programs that need a lot more memory on 32-bit machines, and yes, they start clashing into each other. Or if you have a recursion that's out of control, then stacks keep growing, hits the heap. Right? Or you have heap allocation that never frees anything. Of course, it could crash into the stack. Right? That would be bad. But OSs with a little bit of hardware support could support these bounce checking. So if it hits some watermark, and OS can actually get notified and warn the user, do you want to still do this? Or OS could intercept it and actually do a debugger dump to the OS and to the user core dump file, and that way they can use a debugger to figure out what's going on or give them some message. Okay. Anyway, with this kind of usage, ideally you would use memory from two extremes: one from bottom up, one from top down, and the blue chunk in the middle are supposed to be mostly empty. In fact, you probably expect most programs to use a small percentage of your address space, and you have most of the middle part, that big hole, is underutilized. So you never really need to fulfill those. You never really need to allocate real physical memory to those. Okay, and then of course as stack grows, as you make more function calls, stack grows. Then more pages could be allocated to it, right? And that's fine. And then as the stack gets popped, those pages can be taken back, right? And another thing is with shared memory. So let's even just look at code. Most OSs wouldn't allow self-modifying code, at least outside OS. OS itself could do self-modifying code, but user shouldn't be able to. And that's actually nice. Why? Because then by enforcing read-only, this allows the code to be shared across processes, especially code, right? You could imagine on a shared machine, lots of users could be running the same program in different processes. Do you really need to load different copies of the code? Well, you do need to put them in their own address space, but then the actual physical memory just needs one copy, right? So that way, you just by mapping, you actually save the time for loading Next time you spawn another process of the same program, hey, the code is already there. You don't need to load anything, right? So just establish your mapping and you're ready to go. Okay, and so that so oftentimes that's a consideration when you do like a fork. Okay. All right, and so share pages doesn't have to be just text or code. Could be share pages or share libraries. And shared libraries may be mapped to different locations. Probably wouldn't be the bottom, probably somewhere above heap. In any case, share data, share library, they just need one copy, and the virtual memory system can take care of mapping. So that allows you to utilize the memory resource very efficiently. Okay, so as you recall, this was mentioned, swapper versus pager. Swapper, or the idea of swapping is if you run low on physical memory, older OSs would move the entire process from memory to disk, and then that frees up lots of physical memory that you can use for other purposes. Nowadays, most OSs don't do that kind of swapping. Instead, they do a specialized kind of swapping on just pages. Okay, and so we don't always call them swapper. Occasionally, you see the word swapping here, but really, when you're talking about modern OSs, swapping refers to paging. And by paging, this means paging to disk and back. Okay, so using some of the same ideas as swapping, but limited to just the paging part. Okay, and so this idea is the same. When you run low on physical memory, what a pager can do is to do a page out. That is, save the page onto disk, remember where it is, so that that frame is freed up. Then the frame could be assigned for some other purpose, right? And then if the user code runs and then runs into needs to fetch or execute some instruction that's not currently resident, but is on memory, then there's swap in. The OS takes control, swaps in, that is, read from where it's saved it on disk into that frame, and then, well, you may have to re-update the virtual memory, the mapping, then resumes so the program can run. And this is all transparent, supposedly transparent to user program. The only way user program can tell is there may be a delay, like a hiccup, like another 100 millisecond delay. It's like, hey, what happened? 100 milliseconds disappeared. Well, got transplanted or transported over time to a point in time in future. That's because OS takes care of restoring that page. Okay, so as you can see, this kind of saving, restoring that concept is done repeatedly throughout different parts of OS. Right? We've done like saving registers, restoring registers. Now memory pages can be saved and restored, but only now it's done to disk or swap space. Okay, a special case of paging is called demand paging. Okay, and this is a way of implementing virtual memory by doing what's called, you might call lazy evaluation. And you've seen lazy evaluation, right? In computing, lazy evaluation means you don't have to, or you try not to do, you procrastinate, you don't evaluate something until you absolutely have to. Then you evaluate. Same idea with paging. So as you may imagine, a pager could be a little bit more proactive, or it could be saying, well, I'm just going to load in the entire program in, right, or the entire memory. That wouldn't be demand paging because that's just doing straightforward paging. Demand paging says, I'm only going to set up some mapping and then indicate where things may be or things not defined. And so as needed, and the user executes some code, and the code is not in physical memory, what happens? Well, OS takes control, and that's called page fault, and handles page fault by loading in that content into memory, then allowing the program to continue. Okay, so that's demand paging. And this could be done on program, on shared data read-write, or read-only, whichever, right? So it really doesn't matter. But if it's read-only, then there's benefits of doing sharing there. So benefits to demand paging is you don't do I/O until needed. So in terms of I/O count, you are much closer to optimal, and also you're using up less memory than needed because you don't use memory until the user actually issues an instruction to do it, right? And it can be faster response because you can start up and running as soon as the memory you need is in the physical memory, right? And so by using up less memory, that means more memory is available to share across different users, right? Lots of benefits there. And of course, there's downsides to it. That is, startup costs tend to be higher, right? Because when you start running, oops, nothing is in memory. So at least if you're the first one, so you end up getting lots of page faults. You run, do a number of things, and page faults again, another one after another. So you get a bunch of page faults all bunched up in the beginning. But then it warms up, and then it'll run smoothly. And then with other optimizations, it can be made efficient. So demand paging is actually what's used nowadays. But there's different variations of it too. Anyway, some basic concepts. So you do need MMU support. And in fact, what you did for just basic paging the previous chapter version of paging doesn't involve writing to disk, right? But if you need to write to disk, that MMU has to be different, has to be enhanced, has to be augmented with additional features. Otherwise, it's not going to be able to fully support demand paging. So yes, hardware enhanced features are required. And now if pages are already memory resident, then demand paging, non-demand paging, no difference, right? Because you just access memory directly. But if the page is needed but not memory resident, then demand paging does require the OS to take control and do the loading into memory, update the tables, and then do what's called instruction restart. And I'll talk about that in a little bit. So that was a feature that a regular non-demand paging didn't need, but demand paging does need that. Okay, but demand paging allows you to provide this nice abstraction because user code doesn't really have to be written in a way that's aware of demand paging. Whereas in other kinds of paging, if you actually try to access a page that is not memory resident and it's put out to disk, then oops, there's no mechanism to handle that. It would just say, oh, that's an invalid page, and then abort. But demand paging does require kind of a stretched interpretation of what valid, invalid means. Okay, valid is still the same, but invalid has additional meaning. Anyway, so demand paging can be written in a way so that user is not aware of any demand paging going on. And so you don't have to change your code at all, okay? And user doesn't have to, and program would not behave differently. OS takes care of all of that. Okay, so let's revisit valid and invalid bit. As you remember, page table and also these MMU, more specifically, your TLB, would have these valid and invalid bits. And so these are bits associated with each table entry. So it has two values, and usually we use a symbolic value, V and I, but in practice it's a 0, 1. So V means valid. That means it's memory resident. Go ahead, proceed. No difference. Okay. So the traditional non-demand paging works this way as well. Now, what if it's I? I is invalid. Well, there's actually two possibilities. So the older possibility means, well, it's an invalid reference, right? Because it may be a part of the memory that OS really hasn't allocated. And it's not stacked where you can grow, and OS knows about that. It may be where you have a heap boundary, and it's in that big hole that hasn't been designated yet. So if you try to access that, well, sorry, you can't. It's considered invalid. Okay, and there's not even a mapping for it. So the only reasonable thing for OS to do would be to abort. Okay, that's with a non-demand paging. But with demand paging, well, that could be one possibility, so it has to handle that too. The other possibility is that, well, it's not in physical memory, but that doesn't mean it's not a valid part of address space, right? It can still be a valid part. So if it's so determined that it's a valid part of your address space, then, well, it's handled as a page fault, and then page fault handler would look up where it's saved on disk, bring it back, fill in that frame, and then allow it to continue. Okay, so that's the difference of how demand paging will handle the invalid bit. So if it's invalid, it does need to check one or two possibilities. Is it the previous case of invalid where it's outside your address space? If so, well, handle like before. It's a really invalid reference and abort. But if it's only because it got paged out, then, well, the OS takes over, handle it as a page fault, and then bring it back to memory, okay, and continue.
So
Yeah.
How you are gonna know that it's invalid and it's in page?
So there's additional data structure to tell you. So part of the, remember PCB, process control block? Yeah, that additional fields in there to tell you, yes. Okay. So yeah, OS does have to have a lot of bookkeeping going on. Hundreds, if not over 1,000 fields per process. Okay, and that's why a process creation is expensive too, because so much more bookkeeping. I mean, before it was simple, and then it grows over, and then it's wow, lots more additional information it needs to maintain, and that's why threads they share that the address space, so it has a much easier time. Anyway, so now valid invalid bit would be all initialized to I. And then the MMU will do the translation, and so if it is I, well, the OS in the demand paging case it has this a way to check and then can handle it as a page fault, and most likely that is the case. And there may be additional fields in the MMU to help you accelerate that lookup. So even part of the page table entry content beyond just frame number and invalid, and read write and process ID, they could also be in the MMU as well. So now page table, when some pages are not in memory, well, you would then have valid and invalid. So valid says, okay, that's a frame number. Invalid says not in there, but additional field either kept by MMU or cached by MMU or the TLB. But certainly your PCB needs to contain this information, so OS can actually go and check in software. Okay, but there's hardware acceleration possible here, and so these are invalid. Okay, and then when it tries to access and assuming it's in the address space, then OS takes a page fault and say, oh, then I'm going to go to disk to load it and then fill it in into the physical memory. Okay, and that way, like for example, A and C and F here, B, it tries to access B. Oops, it's invalid, but it's on disk. So grabs it, fills it in. Okay, and then it could, now how do you choose which frame to fill? Well, that's a separate problem. Okay, so page fault happens when your program makes a first reference to a page that it hasn't accessed before. Okay, and what happens? Well, traps to OS. And the OS looks at another table, usually in PCB, to see, hey, is it outside the process's address space? If so, abort. If not, it finds where it is on disk and then load it in. But before it does that, it has to actually have a free frame ready to assign to this process, right? And where do you get a free frame from? Well, we'll talk about that. But oftentimes, there's something called a free frame list, okay? And so that says, okay, I just have a linked list of these free frames. And if I need one, I just grab it from the free frame. And if some process doesn't need that frame anymore, gives it back, and then add it to the free frame. But there's also different policies as to whether you just in advance divide up these frames across different processes, or they can share across processes. Right? There's different ways to do that. But most likely, these processes are not likely to voluntarily give up their frames. So OS has to do something drastic and has to pick victims. Nobody wants to give up frames? Okay, I'm going to come and grab some from these processes. Okay, and so it's going to pick a victim if necessary, and then by saving their content as needed, and then free up that frame, and then give it to right now to the one that is being served for page fault. It may need to do that. Oh yes, a victim would be most likely. I mean, it could be in your own same process, or it could be from a different process. If it's same process, they share the same table. Yeah, but different process, you have to update that. Right? And if it's your own process, and basically you're fighting against yourself, right? You load in the page, but you have to kick out one of your own pages, and then next thing, oh, you need to have something from the page you just kicked out, and then it loads it back in. But to load back in, you have to kick out another one of your own page. And so it can get into a really bad situation. That's called thrashing. And we'll talk about thrashing a little later in this chapter. Okay, and so reading into frame by a scheduled disk operation, OS updates all the tables, setting valid bit from I to V, and then it has to restart. And that's important. Before, you didn't have to do restart. Before, the assumption was you're mapping logical to physical mapping. That's done, assuming it's there, and anybody who does the loading takes care of the or OS for that matter takes care of that. So when you access, it's all assuming from user anyway, also assuming valid, and there's no such thing as restart. But here, when you already start an instruction, okay? So this is different from your trap or your interrupt, because interrupts happen between instructions, remember, right? After you finish one instruction before you start the next one, that's when interrupt can happen. And when the interrupt service routine is served, what happens? Well, it's the address of the next instruction that got pushed on the stack, remember? Right? And that way, when you resume from that service routine, it actually does the next instruction. But page fault is different. You have a load instruction or add instruction, depending on addressing mode. Then you already started doing that, and then you're in the middle of that instruction. That instruction hasn't been completed, and it couldn't be completed. Why? Because you have page fault. The memory is not resident. So then the OS takes over. But then what happens? Well, it couldn't push the address of the next instruction. It has to push the address of the current instruction. Okay, so that way when it restores, it has to restore and by retrying that instruction again. Okay, you see that difference? That's a subtle difference, but important difference. You gotta realize. Okay, and that does require the instruction or the machine, the processor, to handle this properly. Okay, and so that's why the demand paging support can actually complicate your hardware design. I mean, not a big deal nowadays, but it did take a while for all the support to come in place to support demand paging. Okay, so this is more kind of a flow, right? First is maybe a load instruction, load memory. It's not resident. There's a trap to OS. And I actually enhanced this picture just so that it's consistent with what we talked about. Two cases in OS. Checks if page is not in address space. Is that the case? That's 3B abort, right? That's and then but in assuming it's in backing store, then 3A case 3A goes to disk, bring it back, and then of course while it's waiting, OS should have enough time to find a free frame. Bring in a missing page. But actually, the OS may need to flush out an existing frame. So that's not in this flow, okay? So by picking a free frame, it may actually need to do a write to disk before it can do the step from step 4 to bring in the missing page. Okay, so but I'm just taking this from the textbook to show you the idea. So there's different conditions that may need to be considered. Okay, so that way, but in practice, that's not done because of free frame list. And most OSs ensure that there is actually a minimum set of frames in your free frame list. Your free frame list is never empty. That's what most OSs assume. That way, it actually simplifies this page fault handling because you can easily assume there is some free frame available. But you say, how can you do that? Really? Well, so it actually steals cycles. When the machine is not too busy, it proactively kicks out someone or flushes their content to secondary store, so that when it comes time to reclaim, so then they're no longer considered what's called dirty. They're considered clean, so they don't have to be saved again. So they're saved kind of in anticipatory way. Okay, but we'll talk about that a little bit later. So in any case, the page gets brought in. The page table is updated to reflect the status that now it's memory resident. So I gets changed to V, and needs to restart the instruction. Okay, so it's not the trap doesn't return to the next instruction after the load. It actually retries that load instruction. Okay, that's the difference there. Okay, so now pure demand paging will have some issues when you first start a process. Why? Because everything is going to be a page fault. When you run the first instruction, it's going to be a page fault. I mean, in pure demand paging, right? So even though you can have the mapping, at least it's not in not resident as far as you're concerned. It may be used by some other process. Maybe some other process is already running the code, but you didn't know that. OS then goes and checks, oh, that one is there. And so it can do some optimization by maybe sharing the code pages or text segments. Now, what about data? Well, again, you may try to initialize things, but it may be marked that, yes, that's part of your address space, but it's not in physical memory because you haven't been allocated anything. So page fault. So it's kind of painful for a process to start because they first get the page fault for instruction. Now they have the instruction, they get a page fault on the data, and so it's just one page fault after another. So it can take them some time to start. So, but you have to pay that price somewhere, right? That may still be better compared to loading the entire program and using up a lot of memory to begin with. Okay. So anyway, and also depending on the instruction set, one instruction could cause multiple page faults. I mean, this is more the case in the CISC instruction set. That is, I mean, if you ever programmed, even 8051, that's considered a CISC instruction set, even though you said a little bit 8051, it's not that complicated, is it? Well, it's the formatted instruction that makes it complicated, right? Because it's variable length. Some instructions are single byte, others are 2, 3, 4 number of bytes, right? So and remember, there's like move or even add. It could be from 2 different direct addresses or 2 different or some combinations. So now, if you add 2 numbers from memory and store result back into memory, what could happen? Well, in the case of demand paging, these 2 operands may reside on different pages. So what do you have to do? The program runs, when it loads the first operand, page fault, handles it, and then retries this instruction. So it retries, first operand is okay, second operand, oops, another page fault. Then OS gets control. So the same instruction may be restarted multiple times, okay? That's complicated. And so that's really one reason, one of the arguments made by people who do RISC instructions. They say, well, we keep it simple because we only have to retry a low store instruction at most once. We don't have to retry all the combinations of opcodes and operands. Okay, so yeah, that is one benefit with the RISC instruction set, because they limit the number of possible page faults that each instruction can cause. So the pain is mostly at the start, but then as these pages get brought in on demand, it becomes less painful, right? And because of what's called locality of reference. And so hardware support needed for demand paging may include additional fields in the page table in hardware, right? So valid, invalid bit, possibly with also the address space checking. And now you also need some space on disk, but what kind of disk? Do you use your same file system, or do you use a different partition, use a special disk for that? Well, these have all been considered. So yes, theoretically speaking, you could use the same file system for your swap space, but that's likely to be inefficient. Why? Because later when we look at file systems, you'll see, again, there's lots of things that an OS has to do. It has to maintain the directory structure, file has to have bookkeeping, like the length, the blocks, and their linked, and there's contiguity issue as well. And there's just a lot of abstraction provided by the OS to make it a nice abstraction. But if you use that for demand paging, it's going to be quite slow. So usually what happens is either you partition up your disk with a particular partition that's just for swapping purpose, or you even have a separate swap disk, okay, or swap device. And as mentioned, hardware also needs to support instruction restart. Now, instruction restart, this is just an illustration. It also depends on how complex. We talked about having two operands in the, say, an add or move instruction. But some instruction set, like the VAX, may support block move. That is, you copy a chunk of memory from one location to the next. Now, that can get complicated. Why? Because what happens if the memory you're copying cross memory boundary, right? And what if there's overlap, right? So that means you got to store those intermediate states. Otherwise, you'll be repeating some of the copying operation, or maybe you have to remember where you stopped and got interrupted. So yeah, the instruction restart can be really complicated, and so that's why there's RISC designers think it's really one of the things you do want to make it a little easier. Okay, stages in demand paging, worst case would have to consider all these, right? So page fault traps to OS saves the user register and process state as you expect, just like your little threads package has to save these registers, right, in other process states and stack as well. OS check if illegal reference. If so, then you can proceed to finding the location on disk. If not, it has to do the abort, right? And OS issues a read from disk into a free frame, but it may need to pick one, just depending on how you implement. But here, we're assuming you have a non-empty free frame list. You can take that and then make that the target of your free frame. And then, so whatever you read from disk gets put into that free frame. And while this is happening, and reading disk can take a long time, as far as a computer is concerned, right? So does the CPU just wait there? No. In fact, this can be the time that may be multiples of your quantum, right? Or like your context switch time, your quantum may be like 10 to 100 milliseconds. Well, that's how long it may take to load a process, right? For CPU bursts, that's right around that order. So then CPU would be assigned, so there's a context switch to some other process. Let them run, utilize the CPU. And when disk is completed, usually there's a DMA kind of interrupt. So OS at least registers it. It might not, there's a context switch on the spot, but at least it can do a little bookkeeping and say, okay, now I can put that on like a retry queue or something. And when it comes time, the scheduler says, now I can retry it, then there's a context switch to retry. Okay, so but before then, the OS needs to do the update of page table, allocate CPU to this process, and that's the part of the scheduler. Then once it's to be scheduled or to be dispatched, or restores the user register, process state, new page table, right, and resume. Okay, so that's kind of worst case scenario. So non-demand paging. So that means, well, the page fault is a fatal error. So if the valid invalid bit is I, it's fatal. There's no really other way to proceed other than to abort. Okay, mechanism is between CPU and memory. And, sorry? No, right, this is assuming no disk, right. Okay, or no, even if there's disk, this has to be scheduled so that any kind of swapping, that is to disk and back, would have to be done by scheduling, or OS would have to do this. So, right, so this actually encompasses both no disk case and with disk, right? So non-demand paging actually does mean you need to keep things resident, okay? And so you could do swapping, but swapping the entire thing out. But when you swap back in with non-demand paging, you got to bring everything back, okay? So that way, when it's running, it doesn't cause page faults, right? So it's valid, right? Demand paging, well, the I could mean not part of address space, or could mean page fault. So it's fatal only if it's outside address space, but not fatal when it's just non-resident, but on disk. Okay, so that's one difference you gotta keep track of. Okay, free frame list, we mentioned this. So it's a pool of free frames, and you use some link structure, linked list, whichever. And a lot of these are what's called zero fill on demand. What does that mean? That means you put them on on this linked list, and you don't really need to do anything until you are sure you're gonna give it to some process, and only if needed. Okay, and just before you assign it to somebody, you would zero out. Why? Because if you don't, it can contain leftover data from the previous user of that frame, right? But sometimes there's an optimization where you don't zero fill. Why is that? Because basically what you do is you flush out some content of a page that's been modified to disk, and you put it on free frame list. And that just means it's the memory content is still used, and that just means it's not really resident as far as the page table is concerned. But what if the process needs it again? Well, it's on free frame list, right? You haven't wiped it out. So instead of bringing it back, well, you don't have to, because the disk is the same as what you already have, right? So the content is still there. If that's the case, you can do an optimization by saying, hey, I don't just grab any free frame. This was one that I just flushed out. And so I can skip the reading back. I just grab it from the free frame list. So before, it was using it anyway. And so I took it away temporarily, but I haven't trashed it yet, so I can safely reassign it back to whoever I grabbed it from. Okay, so it was a victim, but I haven't really killed that. And so, okay, sorry, I just grabbed it and now here it back. Okay, so that is that would be a case where you don't do the zero fill on demand. So that's a special case only if you give the free frame back to whoever you grabbed it from. Okay, and its content hasn't been changed in the meantime. So that could be the case. But otherwise, if you give it to some other page, right, then you would have to zero it out.
But the zero fill on demand is going to be when another process will need that frame in the full free
If another process wants it, and it's not a read-only shared page, then yes, they would have to zero it out. If by sharing, you by definition don't want to zero, right? But if you but in the same, even in the same process, you still want to zero it out. Yeah. Okay. So performance of demand paging. Well, there's different costs. There's service the interrupt, as you can imagine, restart the process. That's a lot like resuming, but then that actually can take a while depending on how complex your instruction may be. But most of the time is really with the transfer between disk and memory. Okay, so the swap in, swap out cost. And so now here they use a variable p to denote page fault rate. And the rate, of course, is between 0 and 1. So the effective access time, we saw this formula before, right? And so that is you weigh the memory access time by the non-page fault case plus the page fault case times the page fault overhead swap in, swap out. Okay, so that's how you compute the effective access time. And the book gave an example. This is straight from the book. So if memory access time 200 nanoseconds, average page fault service time 8 milliseconds, or actually it could be much longer, then you have effective access time just depending very much on your page fault rate. Okay, so if page fault rate is like actually 0.1%, so 1,000th, then you have effective access time of 8.2 microseconds. So that is a slowdown of 40 times compared to not having a page fault. Okay, so unlike cache hit, is not going to be that. Cache hit or cache miss is not penalized by that much, even for a hit rate of a similar hit rate. But if you want performance degradation should be less than 10%, then you can work out the math, and so you can see that if it's the page fault rate is what 0.00025%, so 1 out of 400,000 memory access, you get a page fault, then yeah, that degrades your performance by less than 10%. Okay, which is probably reasonable. Okay. But as you can imagine, on startup, if you have clusters of page faults, that's going to be very painful, right? Because that's a lot higher than 1 out of 1,000 accesses.